Hi, Keys Precalculus. We are going over section 2.5 in our book, but this video is 2.5b because I did 2.5 a year ago for the last half of the chapter. So I'm going to start with the first half of the section. In class, we went over the fundamental theorem of algebra. It says if f of x is a polynomial of degree n, where n is greater than 0, that means its exponent is at least, the degree of the polynomial is at least 1, then f has at least 1 0 in the complex number system. So if you've got a degree of 1, then you're going to have at least 1 0 in the complex number system. If you have a degree of 2, you're going to have at least 1 0 in the complex number system. In fact, Gauss in the 1800s proved that from this fundamental theorem of algebra, it can be proved, or it can be derived, that every nth degree polynomial function has precisely n zeros. In other words, a second degree polynomial would have 2 zeros. A third degree polynomial would have 3 zeros. A 12th degree polynomial would have 12 zeros. It doesn't mean that all of these zeros are real or all of them are rational, but they are zeros. They can be in any form, any real number, which includes any rational number, or any complex or imaginary number. But also remember that we learned that complex numbers imaginary numbers come in conjugate pairs. So you would have a plus bi. If that was one of your zeros, then you would also have an a minus bi as a zero. Now, the other theorem that we talked about in class is on page 135. It's the linear factorization theorem. I'm going to talk a little bit more about that in the other video, so I'm not going to go over it so much here. But just remember that if a polynomial has a degree greater than 0, then it has precisely that many linear factors. So if you've got, let's say, a 5-degree polynomial, then we derive by the fundamental theorem of algebra that it can have precisely 5 zeros, but that means it also has precisely 5 linear factors. We're going to talk about that more in the next video, what kind of factors they could be. They might be real and rational, they might be real and irrational, or they might be imaginary, or what we call complex. We did example 1 in class to illustrate the fundamental theorem of algebra, or to illustrate the idea that if we've got a second degree polynomial, it has 2 zeros. We're going to do it again on example 2. Example 2 on page 136 says justify that the third degree polynomial function f of x equals x to the third plus 4x has exactly 3 zeros, and it lists the zeros. And so what we're going to do is we're going to show that it has exactly 3, and the way we would do that is we would factor this polynomial. Those two terms have a common factor of x. So I can factor out an x here, and I'm left with x squared plus 4. So here I have 2 factors, but they are not linear factors. Okay, we need to create 3, because the power is 3, linear factors. So I also have to factor this second binomial, x squared plus 4. So my first factor is x, my second factor is x squared plus 4, and I can factor that again. Now, there's a few ways to factor this. Obviously, if I factor it, I'm not going to get real numbers. I could use the quadratic formula because I've got an x squared here, or I can treat it as x squared minus, a difference of 2 squares, x squared minus a negative 4. I can treat this as a difference of 2 squares, which would be x plus the square root of negative 4, which is 2i, times x minus 2i. Because remember, the difference of 2 squares, a squared minus b squared, factors into a plus b, that's the square root of the first term, divided by plus the square root of the second term. So a minus b. So it factors into a plus b times a minus b. Square root of x squared is x, so that's why I have my two x's right here. And the square root of negative 4 is 2i. If you need to see that over here, remember that's the same thing as saying negative 1 times 4, which is the same thing as saying negative 1 times 2, which becomes 2i. Okay, so here's my three factors, and if it's got three factors, then it's got three zeros. Here, x equals 0, and if I solve for 0 for each one of these, x is going to equal negative 2i for the first one, and x is going to equal positive 2i for the second one. So I have just shown that this third degree polynomial has exactly three zeros. By factoring three factors, I could solve for three zeros. Let that sink in for a minute. Okay, now let's look at example 3 on page 136. It says, write this polynomial as the product of linear factors and list all the zeros of f. Now, this example is going to combine everything we did in the last section, actually the last couple of sections. We need to use the rational zero test, synthetic division, and factoring. Okay, so let's go ahead and start with the rational zero test. We'll say that if this polynomial has any rational zero, they will be of the form p over q. P is the constant and q is the leading coefficient. Now, because my leading coefficient is 1, I don't really need to look at that. All I have to look at is the factors of the constant. So those factors are positive negative 1, positive negative 2, positive negative 4, and positive negative 8. I've got 8 possibilities here for rational answers, rational roots. They may not all be rational. I've got 5 roots or 5 zeros, but they may not all be rational or even real. But if they are rational, they'll be from the numbers positive, negatives, 1, 2, 4, or 8. I can help limit my choices or narrow my choices by using Descartes' rule of signs. So let's go ahead and do that. But before I do that, I'm going to make my little chart like we were talking about in class. I can have positive answers, I can have negative answers, I can have complex or imaginary answers for my total number of answers here. So I'm going to make this little chart. I think y'all did this in Algebra 2. My total answer has to add up to be 5. So if I look over here at my changes of sign for f of x, there's a change of sign here and a change of sign here. So I can have 2 or 0 positive solutions. Now let's look at f of negative x. Remember, the sign only changes if my exponent is odd. So this becomes a negative x to the 5th minus x to the 3rd. This one does not change, 2x squared. This one does change, plus 12x. And my constant does not change. So for my negatives, there's no change. There's a change here, and there's no other change. So I could have 1 negative. So I could have 2 positives, 1 negative. That means I'm going to have 2 imaginary numbers. Or I could have 0 positives and 1 negative. That means I'm going to have 4 complex answers or complex roots to get a total of 5. So that's it. This chart, and by using Descartes' rule of signs, I see that I'm going to have some complex answers. I will either have 2 of them or 4 of them, because as we said before, complex answers or complex roots come in pairs, conjugate pairs. Another way to narrow my choices is to look at the graph of this function. So let's go over to Desmos, and poof, we're magically here. As you can see, this graph crosses the x-axis in 2 places. So this would lead us to believe that we have 2 real zeros and then 3 imaginary zeros. But we know that we cannot have 3 imaginary zeros because imaginary zeros have to come as pairs. So I'm going to have either 2 or 4 imaginary zeros. And when I come back and look at my table, I can see that that's true. I'm either going to have 3 reals and 2 imaginaries, or 1 real and 4 imaginaries. Now, because my graph shows that it crosses the x-axis more than one time, I know that I can't just have 1 real 0. So I know that this is not going to be the case. I'm going to have 3 reals, 2 of them positive, 1 of them negative, and 2 imaginaries to have a total of 5 solutions. So let's look at our graph one more time. Looking at this graph, we see that it crosses at -2, 0 and at 1, 0. So I know I've got zeros there. One of these is a repeated 0. One of them has a multiplicity of 2. Now, I told you a little bit wrong in class today. I want you to look back on page 104 at the repeated zeros definition. Basically, if you're going to have a repeated 0 that crosses the x-axis, it has to repeat an odd number of times. If you're going to have a repeated 0 that touches the x-axis, it's going to have to repeat an even number of times. Now, I've got to have 3. So I can't have 1 of these and 2 of these. I can't have 1 at 1, 0, or 1 at the positive and 2 at -2, 0, 2 of the negatives, because I know I'm going to have 1 negative answer and 2 positive answers. But also, if you look on page 104 at the definition of repeated zeros on a graph, you will see that because if it was to cross it, I would have to have an odd number of repeated zeros. So I'd have to have 3 or 5 or 7 or whatever, and I can't. But if it touches the x-axis and goes back up again, that means I have an even number of repeated zeros. So I know I have to have 2 positives and 1 negative, so I know that my repeated 0 is going to be at 1, 0. So we're going to show this all by synthetic division. Let's go back to our work page. By the graph, it appears that our zeros are going to be at +1 and at -2. And I need to show that with synthetic division because I've got to get this x to the 5th down to an x squared. So I need to do synthetic division 3 times to get this down to an x2. So I'm going to start with my -2 and put that in the synthetic division box. My coefficients are 1. There's no x to the 4th, so I need to put a placeholder. There's a 1 for the x to the 3rd, a 2 for the x squared, a -12 for x, and an 8 for the constant. So let's say 5, 4, 3, 2, 1, 0. Yes. And I'm going to draw my line because this is where I'm looking to make sure that that's a 0, to see that -2 is actually a 0 of this function. So I'm going to bring down my 1. -2 times 1 is -2. 0 plus -2 is -2. -2 times -2 is 4. 1 plus 4 is 5. -2 times 5 is -10. 2 plus -10 is -8. 2 times -2 times -8 is +16. -12 plus +16 is 4. -2 times 4 is -8. And I see that my remainder is 0. So -2 is a factor. Excuse me, -2 is a 0. X plus 2 is a factor. Now I'm going to do the same thing, synthetic division, on one of my 1s. And I'm going to do it just on these answers that I got from the first synthetic division instead of rewriting everything again. So I'm going to bring down my 1. 1 times 1 is 1. -2 plus 1 is -1. 1 times -1 is -1. 5 minus 1 is 4. 1 times 4 is 4. -8 plus 4 is -4. 1 times -4 is -4, and -4 plus -4 is 0. So far I've got my factors as being x plus 2. That came from this one, the first one I did. And x minus 1. That came from the second one I did here. I have determined that 1 is a repeated factor, so I've got to do it again on the next set. Because here, in this set right here that I'm putting an arrow to, that goes from x to the 5th down to x to the 4th. Can't factor that easily. Then this one goes down to x to the 3rd. Can't factor that easily. I want to get down to an x squared that I can factor. So I'm going to do again, but I also know that 1 is going to be a root because I can see that from the graph. So I'm going to do it again. So bring down my 1. 1 times 1 is 1. -1 plus 1 is 0. 1 times 0 is 0. 4 plus 0 is 4. 1 times 4 is 4, and negative 4 plus 4 is 0. So I see again that x minus 1 is another factor because x is a repeated root. So I've got 3 factors, x plus 2, x minus 1, and then the last factor, all I have to do is put my variables here. This goes from 5, 4, 3, and this is x to the second power. So this is going to be 1x squared. I don't need to show my x, my square, excuse me, my 1. I need to show my x. Plus 0x. I don't have to show my x there. Plus 4. That's my constant. That equals f of x. Okay? If I multiply all those together, I get f of x. But this one, I need to factor. I need to factor my x squared plus 4. This works the same way that I did example 2 when we had our x squared plus 4. I can factor this. It's not factorable in the real number system, but I can use the quadratic formula, or I can write this as a difference of 2 squares. Again, I'm going to do it again over here. This is the same thing as saying x squared minus negative 4. Okay? And remember, a difference of 2 squares breaks up into a plus b times a minus b. So my 5 factors are x plus 2, x minus 1, x minus 1, and then x plus 2i, x minus 2i. There's my complex conjugate answers. Okay? So those are my 5 factors. Excuse me, my 5 factors. So my if I set this equal to 0, the whole thing equals 0, then I can find my zeros by saying x equals the set that includes 2. Actually, you know what? I was wrong. It's not 2, it's negative 2. So sorry. Negative 2. 1. 1's repeated. I don't need to repeat it in my answers. And then positive and negative 2i. Oops, that should be a brace right there, not a... So I write my set like that. However, if I really wanted to list it out, x equals negative 2, x equals 1, x equals 1, x equals 2i, and x equals negative 2i. If I wanted to write out my 5 zeros like that, I could write it like this as well, to show that I know that there are actually 5 zeros. Okay, this one has a this one shows my set. This has a multiplicity of 1, this one has a multiplicity of 2, and this is 2 separate answers. So 1 plus 2 plus 2 is 5. All right? You'll see how that works? Let it sink in for a minute. Pause the video if you need to, and then we'll move on to another example. All right, if we look on page 137 at example 4, it says find a 4th degree polynomial function with real coefficients that has negative 1, and 3i as zeros. Now, again, negative 1, and 3i are our zeros. If 3i is a 0, what else do we know? We know that its conjugate, negative 3i, also has to be a 0. And here I have 1, 2, 3, 4 zeros. This negative 1 has a multiplicity of 2. It occurs twice. So if negative 1 is a 0, then x plus, or x minus negative 1, which gives me x plus 1, is a 0. But it occurs twice. So I could say x plus 1 squared, and then times x minus 3i, because x minus 3i is x minus 3i, and then x minus a negative 3i gives me x plus 3i. So my function is equal to sum a times x plus 1 squared times x minus 3i times x plus 3i. Now, this a can be any number. I could put a 5 in there, I could put a negative 12 in there, I could put a square root of 3, I could put whatever I want in there. because there are infinite number of polynomials that have these 4 roots. Those infinite polynomials are going to occur when I change my a. I change this leading coefficient that stretches or shrinks or reflects the graph. But for simplicity's sake, I'm just going to let a equal 1 because they didn't specify to do anything else. Okay? So I'm going to simplify this. I'm not going to leave it in factored form. I want to factor it out. I'm going to let my a equal 1. So I can just write this over here. Let a equal 1 so it can disappear. And then when I square x plus 1, in other words, I multiply x plus 1 times x plus 1, I FOIL it, or because it is I FOIL it, or because these are the same numbers, it becomes a perfect square trinomial. This becomes x squared plus 2x plus 1. If you need to pause the video and FOIL it, you can. And then my two conjugates, when I multiply them together, I'm going to get x squared, and then this 3xi minus 3xi disappears because they cancel each other out, and then negative 3i times a positive 3i gives me it gives me a negative 9 times I squared, which means negative 9 times negative 1, so we plus 9. It is a complex number, or excuse me, it isn't a complex number. The I disappears, but I don't just get it down to one number because I have an x here. Like when we were taking the i's out of our denominators, we didn't have any variables in there. We have the variable. This is the same thing as saying x plus 3i times x minus 3i. When I have the variable, I'm going to end up in the form of a squared plus a squared x squared plus b squared. Okay, the I goes away. So I'm going to have my x squared in there again. And if you need to pause the video and FOIL it out, go ahead and do that. So now what I'm going to have to do is I'm going to have to multiply x squared plus 9 times all of this. I'm going to have to distribute it. And when I do that, I like to do it vertically rather than horizontally. So I'm going to take this x squared and I'm going to multiply it by all 3 terms. And when I do that, I'm going to get x to the 4th plus 2x to the 3rd plus x squared. And now I'm going to multiply everything by 9, and I'm going to line up my like terms. 9 times x squared gives me 9x squared, and then 9 plus 2x gives me 18x, and 9 plus 1, or 9 times 1 gives me 9. So when I add them all together, I get x to the 4th plus 2x to the 3rd plus 10x squared plus 18x plus 9. So now I have a 4th degree polynomial who has factors of, or excuse me, who has zeros of -1, -1, and 3i. And then I also know that it has a factor, or a zero of -3i. Now, the rest of this section I did in the other video. So after you watch this, you can go ahead and watch the rest of the video. I do the rest of the examples. And once you've watched them both and taken your notes on them, then you should be able to have no problem doing your homework. I'll see you on Tuesday.